Right. Good evening, everyone. We had to start lenses the last part today. This lesson we can complete today. And before that, can you check with your notes and let me know whether you have done the applications of total internal reflection? Did I explain this? If you know, if not, can you kindly reply on chat? I explained total internal reflection, right, last week? And I gave a note in your writing book also. Up to 23. Okay, so we have start from 24. Okay, right. Okay, thank you. Right. So application. So I don't need to remind the total internal reflection students. Reflection of light to the same medium, right? Without undergoing refraction. I gave two requirements. So the number 23, two requirements for the light ray to undergo total internal reflection. One is what? Whatever the medium, in the denser medium, the angle should be greater than critical angle. So that means this angle has to be greater than critical angle of glass. That means I has to be greater than critical angle. Second requirement, light should travel from dense medium to a rare medium. That means incident ray has to be in the denser medium. That is the second requirement. Right? Incident ray. That means if you only can, you can copy down using your own words. Total internal reflection occurs only in the denser medium, not in the rare medium. See, we have not because it is like it's easy to remember, like because sometimes they can give questions in different ways. So right, so that's where I stopped last week, and let's see how these applications of total internal reflection students. One important application is what? Total internal reflection is used in optical fibers. Example. Optical fibers, total internal reflection is used inside in optical fibers. For communication, used in optical fibers for communication, internet connection, and some medical devices. Some medical devices like endoscope, right? Used in right under the first use, used in optical fibers. Yeah, I'll come to Shahid. I'll reply your answer after this. Yeah, because lenses, the next part, I'll reply that. Yeah, sure. You're right. Used in optical fibers. Using optical fibers, total internal reflection is used in optical fibers. For what? Optical fibers for communication, to transmit signals in high-speed internet connections, using communication. Communication. As well as you can write communication, then to transmit for transmitting signals in speed internet connection, and communication, comma, for communication, comma, transmitting signals in internet connections, to transmit signal as light, to transmit signal as light, or transmitting signal as light. So here the signal travel as light. Signal as light in medical devices like endoscope. In medical devices, in medical field, or in medical devices. Like what? Endoscope. Endoscope. Other than communication slash, you can write internet connection also, right? Internet connection also, high speed internet connection. In medical devices like endoscope and internet connections. Internet connections. I think if you have no space, you can write somewhere this side, right? So you can see here light entering from one end and light is leaving from the other end. So here light travels at what? High speed. Light travels at a velocity of what? 3 into 10 to the power 8 meters per second. Light travels at a speed of 3 into 10 to the power 8 meters per second. That is why light is used as signal here in optical fibers to transmit impulse of the signal. If you only can label this one, students, this is endoscope. This is the endoscope. You can label this one as endoscope, and this test is known as endoscopic test. Endoscope to observe internal organs of the body. To observe internal organs of the body. Like what? A stomach. Maybe cancers or tumors or ulcers, or even the wounds in the stomach in gastritis condition. They send this camera through the throat, and then the images can be captured to a separate screen, and the doctors can actually, sometimes they do surgeries also looking through this the screen. So it's easy for them to visualize the complications inside the stomach in gastritis condition or the other complication to diagnose even diseases. That is what is this instrument called endoscope, and this test is known as endoscopic test. Endoscopic test. Tiny camera, they pass through your throat. So normally what happens, students, light travels in a straight line, right? Usually light travels in a straight line. But in optic fiber, even though it's bent, right? Normally light travels in a straight line. When even in our day-to-day life, if you can't use a bent tube like this to send light, because light get blocked beyond the bend, it will not propagate or it will not travel. But in optic fiber, so even though it's like flexible and you bend it in different direction, light reached the opposite end because of the total internal reflection. So what is the main reason for using light as signal in optical fibers? Because of high speed. I think in sometimes in advertisement also they advertise this high speed internet connection or fastest internet. That is using fiber optics or optical fibers. Right. So that is one of the main application of total internal reflection. They can ask this in the exam. Actually, I have mentioned 3 uses: communication, in medical field, in endoscopic test, and internet connections, all 3. Okay. Actually, Shahid, yes. Actually, there are 2 layers inside the optic fiber. So the total internal reflection occurs in the denser medium. Actually, it's like it's like kind of a mirror effect. It's not just reflection, total internal reflection, right? Yeah. So you can for your external knowledge, you can Google and see how light travels inside optic fibers and what are the materials used to make optic fibers. You can get some external knowledge, right? Shahid, I'll come to you the previous question about these lenses and how the fire is being made. I'll come to that after this part. We're going to start anyway lenses. Then next one, actually this one, students. So this is not directly related to the application of total internal reflection. This one you can copy down separately. What? Dispersion of light into 7 colors. Right? Dispersion of light into 7 colors. That means rainbow. We call it dispersion. Dispersion of light. Dispersion of light into 7 colors. 7 colors by a glass prism. Dispersion of light into 7 colors by a glass prism. So actually white light consists of 7 colors, students. So you can see here they have different frequencies. So say violet has what? High frequency. That's why violet is deviated more due to, can you put an arrow towards violet, right? Deviated more due to high frequency. Deviated more due to high frequency. Due to high frequency. Deviated more due to high frequency. Right? So that is and red is deviated least. Red is deviated least due to low frequency. That's why actually this happens inside the raindrops also. Next page I have given that. That is occurrence of rainbow. That is a natural phenomenon, and even water mirage in the desert. So all this due to the reflection and total internal reflection. Right. So that is about actually, even though I have given here, it's not actually total internal reflection. It is due to refraction. Then next one, number 2. I'll erase the screen. Number 2, actually, this one you can erase. This is not number 2. This is just additional thing here. This one you can erase. And number 2 is here, right at the bottom. Below first one, this is number 2. This one erase is number 2, right? Then, so number 2, you can write light is turned by, so this is using binoculars actually. Using prism binoculars. Total internal reflection by glass prisms. Right, total internal reflection. Reflection by glass prisms. Example. Now this is inside glass. Look at the diagram here. Inside glass, outside air. This side also air. So this is the this boundary. There are 3 possibilities. Light can travel along the surface like this, or light can bend away from the normal like this. And the third possibility is this. The third one is already given here. So out of any of these possible, but how to decide whether the answer is first or second or third? Here they have given in your tube. Answer is third. Answer is third. The reason is, students, if you want, you can write near this one. Critical angle of glass. Right? Write separately. Critical angle of glass is critical angle of glass equal how many degrees? 43 degrees. It is constant. It is given in the exam, no need to memorize. Critical angle of glass is given in the exam. It is 43. No need to memorize. So then you have to compare the given angle of incidence. That means angle of incidence. That is simple I. So here the simple I is what? 45. That means what? Light is turned by 90 degrees. In other words, light is subjected to total internal reflection as the angle of incidence become what? Greater than critical angle. What is critical angle? 45. What is the angle of incidence here? Sorry, critical angle is 43. Critical angle is 43. It's given 43 and degrees. And angle of incidence here 45. So which one is more? Angle of incidence is greater than critical angle. Therefore, light undergoes total internal reflection. If you can put an arrow to this and write what? Total internal reflection. Total internal reflection. That means light is reflected back to the same medium. Light is reflected back to the same medium. Now, what would be the answer out of this 1, 2, and 3? Please reply on chat, students. If this angle was 43, look at the cursor here. If simple I is 43, between the normal and the incident ray, if it is 43, what would be the answer out of this 1, 2, 3, the red ones? Yes, answer would be, quickly reply on chat. If the angle was, I asked 43, right? Very good. Answer is Vageshan, correct. Very good. Answer is second. That means light travels along the surface separating the two medium. It travels along the interface. If this angle was somewhere like around 40, what would be the answer? Imagine the angle of incidence here, it becomes 40. 40 is what? Less than 43, less than critical angle of glass. Then answer will be the first one. Very good, right? Okay, Shahid, correct. Not third, Shahid. Answer is first one. If the angle was 40, the answer is first one. If angle is more than 43, the answer is 3. So that's why here you are given in your table answer is third one. Like this is what happened. Now, parallel to the students, can you work out the next diagram also? What is this? Normal, right? So here the light travels in a straight, like, as it enters this glass from air, no deviation at this point. The reason is what? It travels perpendicular to the surface. Now, look at the screen, everyone. You have to mark the angle of incidence. That is between the incident ray and the normal. What is this angle? How to do that? Okay, can you please mark here? This is 90. And here, this corner mark 45. This corner also mark 45. Then you can easily get it. Now tell me, what is this angle simple I here? If you know basic maths, you can decide. Like some of the three angles become in a triangle. So some of the three angles become 180, right? So this is anyway 45. Here also 45. Then what is this angle? Simple I. Tell me. Simple I is 45. This also, this is, some of these two should be 90, right? Because this is 45 again. Wait. This is, I'll make a small correction. This one I'll make 45, 90. Yeah, this is 45. Yeah. Should be 180, no? Yeah. This side, it should be how many? It's 90, no? Yeah. Okay. So then this angle will be more than 45, right? This simple I will be more than 40, more than 43, definitely. This is 90, sorry. This is 90 and this is 90. No. This is 90. Wait. This is 90. Okay, I'll highlight. This is 90, not 45. This is 90. And this corner you get 45. Now the question is, what is the value of I here? I'll highlight that green. So that should be 45. Can you understand that? Because this should be 45. Then the other one should be 45 because 45 plus 45, 90. Is that clear, everyone? So then if I is 45, what happens to this? Will this travel like this? No. Will this bend away from the normal? No. What is the answer? It is turned by again 90 degrees up to here. Right? Then it travels like this. Right? It travels like this. What is this called? Total internal reflection. This is called total internal reflection. So not these two. Because angle of incidence is more than critical angle. So critical angle of glass I have given 43. Right. Then at this point, students, look at the screen, everyone. At this point, again, you draw the normal. Right? You have to draw the normal at this point again. What? Perpendicular to the surface like this. So what is this angle now? Again, this become 45. Can you understand that? This become 45. Here also is 45. Here also this become 45. Angle of incidence. Then again what happened? Light is again undergoing total internal reflection like this. Right? I'll highlight the two angles. Angle of incidence with purple color. This is 45. This also 45. So here the angle of incidence has become more than critical angle. Angle of incidence is 45. Critical angle is what? 43. Glass. If you can note down that separately. Glass critical angle of glass is constant. That we can't change. But the angle of incidence we can change. If you want, you can take a laser beam and do it. If you have a glass block like this, you can use a laser beam and do it. There are some videos I'll show that. So since I become greater than C, or in other words, 45 is greater than 43. Therefore, what? Light undergoes what? Again, total internal reflection. Total internal reflection. This is again total internal reflection. That means light is turned by how many degrees here? Light is turned by altogether 180 degrees. Light is turned by 180 degrees total altogether. But here light is turned by how many degrees? Turned by 90 degrees, the first diagram. Light is turned by 90 degrees. Right? Now that's why students, we call them prism binoculars. What binoculars? Prism binoculars. Prism binoculars. Sorry. Shall I read the screen? You have to complete the second diagram. First one is done for you, but second one you have to complete. So basically, it doesn't matter whatever the diagram you are given, students. You have to check whether the angle of incidence is greater than critical angle or not before you complete the diagram. Okay. Then next one, I'll erase the screen. This is what? Total internal reflection in prism binoculars. That is one application. I don't know whether there is given text, but anyway, you should know the applications of total internal reflection. What is this? Total internal reflection in used in prism binoculars. Used in prism binoculars. Binocular. So actually, binocular is used for the magnification, students. Now you can see there are two lenses. The one end of the tube, you have the objective lens. If you want to label, this is what? Objective lens. Objective lens. This is eyepiece lens. Eyepiece lens. There are two lenses for the higher magnification power increase. Now you can see, so your eyes, the gap cannot be changed. Somehow the light entering from the two ends should reach your eyes. Therefore, to direct light rays towards the eyes, otherwise you have to stretch your eyes. You can't stretch your eyes like this. You can't stretch your eyes. If without this prism, what happened? Light will travel in a straight line like this. Then you have to keep the somewhere here the eyes, right? So you can't stretch your eyes. Therefore, light you have to, in order to see wide area, light is received from wide area, but at the end the light rays should reach your eyes. That's why here light is turned by how many degrees? Turned by 90 degrees. Here also light is turned by what? 90 degrees. And this corner light is again turned by 90 degrees. Like that, they use total internal reflection. Actually, these binoculars, there are prisms as well as lenses. Actually, lenses are, objective lens is a convex lens. Convex lenses are used for what? Magnification. Even hand lens, a light microscope, we use what? Convex lens. Convex lens. So they are used for what? Magnification. Used for magnification. used for magnification. Lenses. That's why we use binoculars in a bird watching cricket match, binocular size. So therefore, binoculars, it's an optical device. Optical device. But they will not ask to draw this diagram in the exam. Students don't need to memorize how to draw this. What you have to remember, binoculars containing lenses for the magnification and total internal reflection here. If you can put an arrow and label this one as total internal reflection. What is this? Total internal reflection. Total internal reflection, even here. Total internal reflection. In each prism, the light undergoes total internal reflection. Okay. Right. So, total internal reflection. What are the practical applications in our daily life? Endoscope, the medical device to observe the organs of the body. Even sometimes there's called colonoscopy. They send the similar camera from the other end through the rectum and anus to check any tumors or ulcers or something or cancers or any other complication in the large intestine. Large intestine, rectum, anus, they from that end also they can send the camera, or to observe your food pipe and the stomach, they send through the throat. Right? That is very useful in medical field. And then I told internet connection, we use total internal reflection inside the optic fiber. And other than that, in communication also we use inside the optic fiber, we use total internal reflection of light, and light is used as a signal there. Right? So those applications are very important. They can ask that in the exam under structure. So I said questions if you get a question under this lesson. Then number 25. Not only the man-made devices, students, this total internal reflection using, but they will not ask this in the exam, never to explain. Just remember the natural phenomena. It's a natural, not a man-made one. Natural phenomenon. Due to what? Due to total internal reflection of light. So what happened? Daytime, even no need to go to a desert, even carpet road, around 12 noon when you drive vehicles, you can see what? It shines like water, the surface of the carpet road. When you drive vehicle around 12 noon, it shines like water. It appears like water on the surface of the carpet road. But actually, it's an optical illusion. What is seen is not there. That is water mirage in the desert. What is this called? Okay, right. One natural phenomena due to the total internal reflection, water mirage in the desert. Water mirage in the desert. That is one. Second one, water mirage in the desert. In single we call it miringo. It's an optical illusion. Dushti maya. Optical illusion. What is seen is not there. It's an illusion. The other one, right? Number 2, occurrence of rainbow. That is the second natural phenomenon, occurrence of rainbow. Now, rainbow, students, again, light undergoes total internal reflection inside the raindrop. Can you see? I'll highlight that word here. Light undergo both refraction and total internal reflection. Total internal reflection. What is dispersion here? I'll highlight that blue. Dispersion means what? Light is separated to 7 colors. And this end, it undergoes what? Because actually this happens in the presence of drizzling rain. In Sinhala, we call it hiripada vassa, drizzling rain. So white light enters the raindrop. Inside the raindrop, light is separated back to 7 colors and undergoing total internal reflection and reach the observer. So then they see like, color, like series of bands like in the sky. That is called rainbow. So in the morning, the sun rises in the east, rainbow is seen. Imagine like in the morning, if this is in the morning, sun rises in the, so if it is in the evening, sun sets in the west. Sun sets in the west. So imagine this is west. Imagine this is west. Then what happened? Rainbow is formed in the east. In the morning, The sun rises in the east, the rainbow is forming the west, like that, opposite direction. Rainbow is always forming in the direction opposite to the sun. Yeah, Shahid, it is same as the rainbow colors. Since this happens through a large number of raindrops, you can see like a band, 7 bands of colors. So that is even sometimes, you know, the like sometimes some small ones, they're playing with that soap like stuff. They are making bubbles, like I don't know what it is called, that what they use. Like they fill that bottle with soap like thing and they are blowing. So during daytime around 9 o'clock in the morning in the presence of sunlight, when they do, you can see inside that bowl the nice, like, you know, colors, 7 colors. Same thing happen inside that those inside those drops also. So whatever. But anyway, they will never ever ask to explain how this happens. You just remember the 2 names. I think textbook they have not mentioned even the name, but in case if they ask for MCQs, you should know what it is. Actually, daytime students, the earth is hot. So heated air, what happened? Rises up. When heated air rises up, what happened? The close to the earth surface, the medium is rare. Upper layers, what? It's rare here. Bottom layer is rare. Upper layer is cool layer. That means dense medium. That means what? When moving away from the earth surface, density of air increases daytime. Because the gas molecules expand. Heated surface of the earth, the gas molecules expand and density decreases. Act as a rare medium. Upper layers denser. So that means what? It appears like light traveling from dense to rare. Dense to rare. And it bends away from the normal, and at a certain point it undergoes total internal reflection. So that is called water mirror. But anyway, no need to memorize how to explain or dilemmas how this happens. Just remember it is a natural phenomenon due to total internal reflection. So that's about this total internal reflection applications and natural phenomena. The next one, the last part of this lesson is student lenses. Lenses. So look at here. Actually, lenses, there are 2 types of lenses. One type is called convex lens, biconvex lens or convex lens. The other one is called concave lens. This is convex lens. The other one is concave lens. Concave lens. Remember, students, this convex lens is also known as convergent lens. Converging, no convergent. Convergent lens. Look at here, convergent lens. And this side concave lens is known as divergent lens. Divergent lens. Right. The reason is actually, if you only can write, these rays are called what? I will mark with the red pen. These are called convergent rays. Look at the screen here. These are called what rays? Convergent rays. Light rays get converged by this lens. That's why it's called convergent lens. See, this is a convergent point. This convergent point is also known as what point? Focal point. Focal point. So can you label this one as convergent point or converging? No, convergent point. This convergent point is also known as what? Focal point or principal focus. Focal point or principal focus. And these are called convergent rays. Convergent rays. But this, the other diagram, please label this one as what? These are called what? Divergent rays. What rays? Divergent rays. They are divergent rays. Divergent rays. Is that clear? Therefore, this is called what mirror? What lens? Divergent lens. Can I remember the out of the 3 mirrors, which mirror is divergent mirror? Can I remember? Convex or concave mirror is divergent. Yes. Convex side mirror of the vehicle. The mirrors that are curved outwards. Convex mirror. Side mirror of the vehicle. That is a divergent mirror, right? But lenses, concave lens. Mirrors, convex. Mirrors convex. Lens concave, but both are divergent. Okay. So this also this is called the focal point. Huh? This one is called the focal point. Focal point. Okay. These are actually parallel. Actually, this happens because the incoming rays are parallel rays of light. These are what? Parallel rays. All the rays parallel to the principal axis get converged here. In the other lens, the rays parallel to the principal axis get diverged, but they appear to diverge from focal point. Okay, so this is the two type of lenses we are going to discuss. 3 mirrors, 2 lenses. 3 mirrors, you got 15 ray diagrams. 2 lenses, you get 7 ray diagrams. Altogether, 15 ray diagrams for this lesson. 7 for lenses, 8 for mirrors. So most of the papers, at least they ask 1 ray diagram. They ask in any oral paper. Like sometimes you can get as MCQs also. Last oral paper they ask from lenses also. Now the others, there are some points you have to remember about when you're drawing ray diagram. Sometimes some paper students they ask what they ask to label this, principal axis, focal point, like that. Not only for very easy questions, sometimes to draw the ray diagram, to label, to identify these points. So look at here the next diagram. This is called actually this is called center of curvature. C1 and C2 known as what? Center of curvature. For both, it is valid. Center of curvature. Sometimes this is also known as 2F. If you can mark here, this is also known as second focal point. It is same as 2F. 2F. So that is also known as C1 or C2 is also equal to 2F second focal point or second focus. Main focus or principal focus is F. And can you please label the midpoint here? That is called O. What is O here? Optical center. Even the concave one is same story. What is called optical center? This dot. Look at the screen, everyone. O means optical center. Please label these things. Very important because before you draw the ray diagram, you should know these points. Optical center. And this is called the line which joins C1 and C2, or the line which joins actually that is the center of these two spheres. So the line which joins these two centers known as principal axis. Right? Principal axis. Right. So these are the important points that you are to remember. Actually, students, this focal point will be the half of this length. Half of this gap is known as what point? Focal point F. This is 2F, this is F. If you can mark that also, if you want, you can mark F. Half of this gap is known as F. Right. F is focal point. F is called focal point or principal focus. Okay. Done. Did you all finish copy down? Shall I raise the screen, students? Now I'll come to your question, Shahid. He asked a question at the beginning. What is the question you asked? What is the reason for fire being made by lenses through sunlight? I'll come to that point now, students. There's a practical given in your textbook. Once in the oral paper also they ask this, because about 25% of the questions in your oral science paper come from practicals. Right. Now, Shall I read this? Anyone still coming down? Raise hand. Done, right? Okay. Wait, I'll show the practical now in the textbook. There is some videos also away. This is the practical. Can you see the screen? Turn your textbook page number 128 students. 128 top, there's a practical here. Activity, activity 5.5. Activity 5.5, right? What are the, sometimes they can give this diagram in the exam and ask, what are the objective, what are the aim of this experiment? To find what? Focal length and focal point. To find the focal length and focal point of this lens, convex lens. I given the previous page about this. Yeah, focal point, and you want to check the focal length. Now this is there's a white paper, right? Look at the screen here. There's a white paper. This is a white paper, or you can just take a paper, and this is a convex lens. And you can so imagine this side you get the sunlight, or even at night also you can do it, like if there's a tube light or CFL, or like normal for light in houses we use various lights, even that one is okay. Now what happens? All the rays come. These rays are parallel to the principal axis. These rays are parallel rays. All the rays, can you remember, all the rays parallel to principal axis. Parallel to the principal axis. They get converged to one point. Actually, this happens when you have to move the lens forward and upwards and downwards until you get a very small patch of light. So can you put an arrow until you get a very small patch of light? Imagine if you have a hand lens at home, magnifying glass, you can try this. There's a very small patch of light here. Can you label this one as what? Very small patch of light. Until you get a very small patch of light, very sharp spot of light, you have to move the lens. If you want, you can keep the lens at fixed point position, and you can move the paper upward and downward. So, but you need the you can't do this in the dark. You need the light source, either natural or artificial source of light. Then this point is known as what point? Focal point. So you have to move the lens upwards and downwards vertically. That means you have to adjust the distance between the lens and the paper. How to adjust the distance between the lens and the paper? By moving the lens upwards and downwards. So this point is known as what point? Focal point. This point is known as focal point of this lens. Focal point of this lens. And one more thing. If you take the length or the distance or the gap between focal point and the lens, that gap is known as what? The gap between the focal point and the lens. That means lens, the midpoint, we call it the optical center here. From O to F, this OF gap is known as what? Focal length. But the gap between O and F is known as focal length. I'll put a curly bracket here. You also better label this with the pencil. Can you mark that, everyone, in your writing book? I mean, in your textbook with the pencil, can you please mark this? You can put a curly bracket from focal point to, that is called focal length. Focal point to optical center, or the midpoint of the lens, called focal length. Because when you are given a lens to your hand, you don't know the focal length. You don't know the focal point. This is how you find the focal length or focal point and focal length of a convex lens. This is how you find it. So this one, once in the oral paper, they ask this. I think structure is as I remember. Because rays coming from the sun is very far. Therefore, those rays are what? Light rays coming from the far away object is parallel. Can you highlight here? Sun is very far, therefore the rays coming are parallel. But if you take a nearby object, the rays are like this, not parallel. Okay. If you keep a lamp or something very close, then it's very difficult to get this. Right? Best thing is like you can go out sunny day. Now I will come to the questions. Shahid, your question now you ask how fire is made by this lens. Remember, students, all the heat rays, lot of heat is generated at this focal point. Lot of heat is generated at this point because all the heat rays also what get converged at this point. Get converged at this point. That's why this principle is used in what sometimes in concave mirrors also. And it is used as solar heaters, solar cookers, because all the heat rays get converged to one point in case of concave lenses, so convergent mirrors. So same is that's why you are not supposed to look at. You should not directly look at multimedia projector lens because the light coming from the multimedia projector sometimes it can get focused to your eye lens. Then eye lens can get burned. Right? Sometimes we normally we don't directly look at the sun, solar eclipse, lunar eclipse, also the same. Similar reason. So if you put a lens is not damaged because the light rays are not converging to the lens. The magnifying glass or the hand lens won't get damaged because light rays after the lens only they get collected, Nishahid. It is not collected into the lens. So it is collected after the lens on the paper. So if you put a matchstick here, what happens? After a few seconds, it can get, it will ignite. The matchstick can get catch fire. If you put a matchstick on the paper at this point, or if you put, some cotton wool or something, you can try that with different materials and you can record the time taken to ignite, say, some cotton wool or paper or piece of cloth or matchstick, and you can find the ignition ignition temperature. You can get an idea about the ignition temperature from material to material, from substance to substance. Ignition point or the ignition temperature changes. So materials with lowest ignition temperature will get catch fire first. If you put your finger on the skin here, what at this focal point, what happened? That finger, the cells can get burned. If you keep for a longer period, you can feel the heat. Understood? So this is very important. This practical textbook activity 5.5, they have given how to do it, right? How to do this? You are given the first paragraph. How to do it? How to do it? I'll underline if you can note down. They can ask how to find the focal length of a convex lens. What? Adjust the distance between the paper and the lens until a very small patch of light is formed on the paper. That's what you are right. Keep a lens above a paper and adjust the distance between the lens. How to adjust the distance between the lens and the paper? Yes. How to adjust the distance between the lens and the paper? You can move the lens upwards and downwards vertically until you get a clear patch of light. Remember, you have to pay attention to this activity part because you can get compulsory questions in your paper from these activities. It's very important. Okay, so did you mark here the focal point and did you mark the focal length here, students? Put double-headed arrow, put a curly bracket from O to F vertical distance. So the distance from F to O. Is that clear? All right. Shall I read the screen? In your textbook, please mark parallel rays from the sun, from distant objects. Parallel rays come from distant object, like from the sun or moon, distant object. Always remember that from the distant objects, rays are parallel to each other. So those rays, what? All the rays parallel to the principal axis get converged after the refraction. After refraction, they get converged to one point. That point is known as focal point of this lens. Now, these lenses are, okay, what is your, if you take your human eye lens, that also like this, convex lens. But there are differences between the human eye lens and the normal glass lens, or the plastic one or the artificial one. Human eye lens, students, focal length is not fixed. It is like auto zoom, depending on the object distance. Now, when you are using a magnifying glass, what you have to move the glass, magnifying glass, or the paper, you have to move forward and backward or vertically up and down until you get a clear image. But when someone standing in front of you, you are not asking that person to move forward and move backwards until you see his image clearly. No, that won't happen. You don't need to do it. You don't need to move forward and backward until you get a clear image of the objects around you now. Because the human eye lens, the curvature can be adjusted depending on the object distance. Again, I'll repeat this sentence. Human eye lens is living. These are the other normal lenses that we use in spectacles and all this multimedia projector, microscope, hand lens, binoculars, all these are artificial man-made lenses. But human eye lens, you have two lenses that's living. And there are, you have done, I think, grade 9 science, the structure of the eye, the ciliary muscles, right? And the pupil, the size can be adjusted by the iris, right? And the curvature of the eye lens also can be adjusted by the ciliary muscles. When the eye lens, the curvature changes, the focal length change. Therefore, wherever the object, the lens is going to adjust the focal length and zoom it. Focus it on your screen. My screen is retina, right? Therefore, human eye lens for what images? Real images. Why? The retina acts as the screen. The images that can be captured to a screen called what images? Real images. Images that can be captured on a screen. So, what is the screen of for your human eye? Retina. Retina acts as the screen. If you take multimedia projector, but we can get the image to a separate screen or at least on the wall, because multimedia projector lens also form real images. Are you getting this? Real images by lenses? Yes. But microscope lens, those images you can't capture to a separate screen. Therefore, those images are virtual images. Therefore, lenses will capture to a separate screen. If it's a virtual image, you can't capture that to a separate screen. Okay, can you hear me now? Can you hear me clearly, students? Right. Shahid, okay now? Now, I'll erase the screen. Let's move back to the theory again. I explain this part. Now, there are different type of lenses, students. Number 27, look at here. There are different type of lenses. Some lenses, the middle is thick. Thick. If the middle is thick, such lenses are called what? Convex. Plano-convex or biconvex. But if the middle is thin and the corners are thick, if the middle is thin and the corners are thick, that is called concave lenses. That's how when you are given a lens to your hand, you can check whether it's a convex or concave by you can check the thickness, okay, the middle and the corners. But anyway, those are like common things. Then next one, the ray diagram. The most important part is this. The most important part is this. Actually, concave lens, only one ray diagram. If you want to highlight that, concave lens, only one ray diagram. It's same as convex mirror. Side mirror also we got one ray diagram. Side mirror is what? Divergent mirror. This is also what? Divergent lens. This is also because light rays get diverged. Look at here. Divergent lens. Divergent lens. Because light, this is a divergent ray. Divergent ray. Parallel ray. The parallel one to the principal axis get diverged. Divergent ray. That's why this is called what? Divergent mirror. Divergent lens. This is called divergent lens. Now look at here. You better use two different colors or two different highlighters or red pen and blue pen at least if you don't have a highlighter in your hand now. According to the, the same as mirror students. This is the object. From the object, you have to start two rays. First one, you draw parallel to the principal axis. I will draw it again on this line with two different colors, using two different colors. A ray of light parallel to the principal axis, what happens? It gets diverge. This get diverge. But it diverge. Ray of light through the optical center, midpoint, it travels straight without any deviation. So those are the two light rays that will start from the object. Actually, object, if it is a pencil or something like, non-luminous object, it cannot emit light. So there must be some other, separate source of light. Light should come from a bulb or natural sunlight to this object. From the object, light is reflected towards the lens. Right? That's hard. What are the two rays? The first one is parallel one. Gets diverged. It appears to diverge from what point? From the focal point. This is very important. Appear to diverge from what point? Appears to diverge from what point? Focal point. Look at here. From the focal point F. From focal point. Appears to diverge from focal point. Then the other one, that's why when you direct this in a straight line, the red one, you can use the same color for this. That intersecting point, this is called, if you want to label, this is called the principal axis. Huh? This is called principal axis. Right. Then the blue one, it travels. What is O here, students? If you can't remember, right again here, optical center, right? They can, some papers they ask this, optical center. What is F here? Principal focus, or the first focus. You got the principal focus. And the other one, 2F, is second focus. So if you take the focal length 2 centimeters to 2F, it will be 4 centimeters altogether. Now you can see both the rays, what? The red one and the blue one, after the lens, they get diverged. They get diverged. So do they meet the other side? They never meet. They move away from each other. But when you direct them in, when the red one, when you direct it back in a straight line in the backward direction, you can see the intersecting point. That is the point where the image is formed. Look at here the image. I'll highlight the image. This is the object. Object and the image. This image, student, it is smaller than the object. Can you see? Image height is less than the object height. Look at the image height and the object height. Therefore, the image is what? Okay, let's write the properties of the image now. Complete the blanks. Look at the screen, everyone. Look at number 28 blanks. Right? Number first property of this image, smaller than the object. Smaller than the object. Number 2, second one, it is erect or upright. Object is, image is erect. Erect, or you can write upright. Third one, you can write image is virtual or real. Tell me. Okay, reply on chat. You learn about virtual images and real images. You learn on the mirrors also. Is this a virtual image or real image? I told you the real images, the light rays, real light rays should reach towards the image. For this to become real image, the real light rays, not dotted line, real, both the rays must be real rays. Is that clear? Not a dotted line. Not a dotted line. So this image, yeah, good. I got the correct answer from Bhatika Muhammad. Very good. Sasini, is this real? That means you can put the screen here and get it. A white paper or something between O and F. No, this is a virtual image, students. This is not a real image. Look at the first page of this lesson. I gave first page at the very bottom. As I don't know if you can remember. As I remember, I asked you to write plane mirror, convex mirror, and this lens. But this lens means the one that we are doing now, concave lens. Again, I'll repeat. If you only can write down that again at the beginning of this lesson, the first page bottom, first page in the sense the unit 5, the beginning, or in the writing book, what? Plane mirror, convex mirror, and this one, concave lens. Again, I'll repeat. Plane mirror, convex mirror, and concave lens. Always form what images? Virtual images. Always. They never form a real image. Even if you keep the object at different places, the properties of the image won't change. That's why, students, there's only one ray diagram for what? Concave lenses. Concave lenses, only one ray diagram. What are the two rays? Ray of light parallel to the principal axis appear to diverge from the focal point. That is the red one. Then the blue one is what? Ray of light through the optical center travels straight without any deviation. So they don't meet in front of the lens. The image also form the same size of the object. That means this image is not real. It's a virtual image because you can't draw a straight line, continuous line. That's why dotted line. Look at the red one, dotted line. So understood now why it is a virtual image, everyone. The next one, this image is from what? Between O and F. That is also important. Form between O and F. Formed between O and F. Or you can write within the focal length. Image is formed between O and F. So these are the properties of the image formed by concave lens. If you want, you can write only one ray diagram for concave lens. Okay, I'll put an arrow towards this, right? There's only one ray diagram for concave lens. Because properties of the image, Shahid, you have a question to ask? Right. What? Only one ray diagram. Shahid, you must be copying down, no? Please raise hand, those also copying down. Okay. When you're done, you can lower your hand. Keep your hand raised if you are copying down, right? Only one ray diagram for what lens? For the concave for concave lens. Only one ray diagram. Only just write only one ray diagram. That's enough. Why there's only one ray diagram for this? Even you bring the object more and more close to the lens, students, these properties won't change. That's why the properties, right? If you want properties of the image formed by concave lens, properties of the image formed by concave lens do not change with the position of the object. Again, I'll repeat. Properties of the image do not change with the position of the object. Therefore, there's only one ray diagram for concave lens. But the next one, the convex lens, students, there are 6 ray diagrams. Okay. So quickly copy down before I erase this. And when you're done, please lower your hand. Hurry up, student. But you better write down using your own words anything else that you want here. Because later, after a few months, when you look at this, can't be like Greek. Okay, others also copying down. Okay, if you're copying down, no problem. You can take time and do it, but you have to complete or not. Okay. Then next one is students. Shall I erase the screen? Okay, wait, I'll show you a small video clip about this lenses thing. About 5 years. Cave lens. Convex lens. Concave and convex mirror. Did I show this previous class? No, none of these. Okay, I'll show you this total internal reflection here. This one. I have shared today, I will not do it today itself, but I have shared students, unit 6, the digestive system, theoretic PDF also. You can keep this ready for next week. Next unit 6 biology, that is one of the longest lessons, system lesson. Now this is what I taught. Look at the screen here. This is very interesting. You can use a laser beam. You can use a laser beam. Wait, now can you see what happened? Light rays undergoes what? Look at the screen, everyone. Did I show this last week? No, right? Did I show this last week? Yes or no? Otherwise, like no need to. No, right? Okay. So here, student, this is a laser beam, and there's a semicircular glass block. Look at here. This is a semicircular glass block. Semicircular glass block here. So semicircular glass block here. Now you can see what? Ray of light. So after that, this is inside glass. What happened? It is refracted. Now what happened? But this is the angle, right? This angle of incidence is the normal. So this angle of incidence gradually what happened? It increases. It increases. Then what happened? Now you are moving the laser beam away. You are moving the laser beam away. Then what happened? Angle increase. Gradually angle increases. When it becomes more than critical angle, light travels along the interface. When I become C, it travels along the interface. When I become greater than C, it undergoes total internal reflection. Okay, I'll play the video. You can watch it now. Can you see when the angle of incidence increase, what happened? Angle of refraction also increases. Here, R also increases. It's very interesting. Now, wait. Now, what happened? Angle of incidence also increase. Angle of refraction also increase. Now, look at here. Look at here. Look at it. Wait. Now, total internal reflection. I'll move back. Now, you can even try this at home. I increase, R also increases. When I increase, R also increases. So there'll be a time this travels undergo, it travels along the surface. That is like, now this is total internal reflection. This is what? Total internal reflection. Can you see the screen, everyone? So here INR same. So here I has become what? Greater than critical angle of glass. So this is total internal reflection. Got it? So this is the incident ray. This is what? Semicircular glass block. Semicircular glass block. I think you copy down this like that is diagram I gave, right? Last week. When there's a semicircular glass block, there are three possibilities. Can you remember? That one I think I explained. I can remember this. And then you draw the normal here, and there are three possibilities. It can travel along the surface, so it can bend away from the normal low. It can undergo total internal reflection like this. I gave these three, right? Last week not? Okay, right. Bhatika, okay, Shai, correct. Very good. No, oh, yes, Shai, I gave, right? Yeah. So that's what you are doing here. That's what you are doing here, the experimentally. You need a laser torch or something, you can do it. Is that clear, everyone? This is total internal reflection. Right. I don't know how many of you have done this in the school, but even you can measure the angle, right? You can measure the angle, you can see, you can measure the angle. What is the angle here? Check this figure and tell me the angle of incidence here, everyone. What is the angle of incidence here? Here 0, 10, 20, 30. It's around 40, no? It's around 40. I don't know whether it's a plastic or glass one. It's around 40. Then angle of reflection, this one 40 degrees. This side also, what is the angle? This is a laser beam. It's a laser beam. R also 40. Yes, very good. R also 40. I also 40. So this is called what? Total internal reflection. This is the laser beam. This is the incident ray. This is the incident ray. Is that clear now? So gradually, again, you will you can move the laser incident ray toward this side. Look at it. So then when I increase, what happened? R also increase, but I and R equal or less. I and R equal. Now what has happened? It is perpendicular to the surface. Now it is wait. Now it is perpendicular to the surface. This is very interesting. If you can try even at home this. You don't have to go to the school to do this. Even if you have a laser torch and a semicircular glass, you can try this at home. Wait. Now it travels along. So that means this angle is 90 students. That's the reason. That's why it travels straight without any deviation. No refraction. But again, when you're moving this laser torch or the laser beam this way, again you will undergo the same experience. Now what? Still what? This I become what? More than critical angle. Until that, the light undergoes what? Total internal reflection. Now here the I has become what? Greater than critical angle. Any value above C. Now you can see when I become less than C. When I become less than C, the light will undergo normal refraction. Now still what? Total internal reflection. Now also total internal reflection. Now still what? I become greater than C, critical angle of the medium. Now you will gradually observe when you reduce the angle more and more, when I decreases, now what has happened? Now look at the screen. Now what has happened? Now what can you say about critical angle and refracted? Now it is not total internal reflection. Now it is refracted ray. Please raise hand those who had done this in the school. You mark the light. This is the real practical, like the laser torch. You can use laser beam here. Anyone done this in the school? So this is what? Incident ray. Incident ray. So you can measure the angle. What is the angle of incidence here? What is the angle of incidence? Tell me. Look at the diagram. Look at the screen, everyone. What is the angle of incidence? Hurry up. You can mark this on the paper and you can try this. It's 30, right? It's 30, right? It's 30. What is the angle of refraction here? R. Yes, students, what is the value of R? Can you tell me? R is? I is 30. R is? Yeah, I 0, 10, 20, 30. Yeah. I equal 30 degrees. And here R equal? R is 50, right? Yeah, it's 50. So R is what? Greater than I. R is greater than I. Because R is in what medium? Rare medium. I is in which medium? Denser medium. Actually, you had to mark the angle inside, right? Not outside. Inside the glass. Is that clear, everyone? So remember, students, always what? The angle is in the denser medium. What? Glass, this is glass. Glass is the denser medium. So the angle in the denser medium is what? Lower. Angle in the rare medium is what? Higher. Is that clear? Okay. It's not a big practical. You don't need to go to the lab. Even you can do this at home. Or even in your classroom also you can, try this. You can have different shapes of glass and you can try. Even now you can take a rectangular shape. You have a lot of glass blocks in your oral science laboratory, right? Then next one, okay, I think that's okay. So then next one. There's one more thing. Wait. That's right. There's one more video. What is this? Loss of reflection. The lenses mirror, ray diagram for mirrors we have to study. This is what? Look at the screen, everyone. This is what? What is this? Demonstration of what? This is a mirror, student. I don't know whether you have done this prior. This is a mirror. There's a mirror here. So you keep the mirror. What mirror? Plane mirror. Plane mirror. Plane mirror. Plane mirror. You can see gradually. You can again the laser torch. You can use the laser torch and try this. I don't know whether you have done. This is the incident ray. This is the reflected ray. So again, what happened? Angle of incidence equal. What is the law? What is the first law of reflection? Angle of incidence. The second law. Angle of incidence equal angle of reflection. Here 75. Angle of reflection also 75. So you can prove this. Okay. Then next one. Ray diagram for convex lenses. Now next one we have to start convex lenses. Well, I have show this one. Okay. Number 29, before you draw the ray diagram for lenses students, you should know these rules or the basic principles used to draw the ray diagram for convex lenses, because concave lens no need any rules because just only one ray diagram. But next page I have given convex lens 6 ray diagrams. 6 ray diagrams. Look at the screen. Rule 1. What is O here? If you don't know, write optical center. After that, I'll show the video clip. O is optical center. Optical center. Now remember, a ray of light through the optical center travels straight without any deviation. Right here. Rule 1. A ray of light through O. Through O. O means optical center, comma, travels straight. Travels straight without any deviation. Without any deviation. Deviation in the sense without any refraction. Ray of light through O travels straight without any deviation. Rule 2, because some papers, I think last year, all the papers they gave what? Incident ray they gave, and they asked to complete this. Look at the pink one, rule 2. They give the first part, and the other half you have to complete. Sometimes they give questions like this, right? Rule 2 is what? Can you remember the convergent point? Earlier we discussed convex lenses, convergent point. What happens? What has happened here? A ray of light parallel to the principal axis. Look at the screen, everyone. A ray of light parallel to the principal axis passes, refract a ray of light parallel to the principal axis. Is refracted through the focal point, or passes through the focal point after refraction. Refracted through the focal, refracted through the focal point. Is that clear, everyone? A ray of light parallel to the principal axis passes through the focal point after refraction. If you can highlight the ray with a different color, incident ray, and then the this one, refracted ray, like that. Here O is optical center. This is principal axis. These points earlier also I told the same thing. Here the principal axis. Then rule 3. So most of the time, what we combine the first and the second rule to get the ray diagram. Look at this number 3. Number 3, rule 3. Actually, that is the opposite of the previous one. That is the opposite of the second rule. A ray of light through O. O means what? Sorry, a ray of light through the focal point. A ray of light through the focal point. What has happened? Ray of light through the focal point is refracted parallel to the principal axis. Okay, can you please write it? A ray of light through the focal point. A ray of light through the focal point. It's refracted. The ray of light through the focal point is refracted parallel to the principal axis. Exactly. The ray of light through the focal point is refracted parallel to the principal axis. Now, find the focal length of convex lens. That's what I explained before. Now you have to write it without my help. Can you try this without, I think that earlier textbook also I told this. Okay, shall I read this? Did you all finish copy down, students? 3 rules. What is the use of these 3 rules? To draw the ray diagram for the images formed by to draw the ray diagram to obtain the image formed by convex lenses. Those are also copy down. Please raise hand when you're done. Please lower your hand. Hurry up, students. Here, through the focal point in the sense, so the principal focus, the main focal point. Okay. Next one, find in the okay. First, try the method. Adjust the distance between what? What is the method or the procedure here? Adjust the distance between the lens and the paper until a very small patch of light is formed. Until okay, wait, it's there in your textbook also, the activity. This activity is bit important. Hold a convex lens to sunlight and place a white paper in front of the lens. You can write that in 2 steps. Hold a convex lens to bright sunlight and place a white paper in front. Hold a convex lens to bright light or bright sunlight and keep a paper in the opposite side. Keep a paper in front of the lens. Then second point, what? Adjust the distance between second writer, adjust the distance between what? Between what? Between the paper and the lens. Between the paper and the lens. Between the paper and the lens. Until a clear patch of light, until a small patch of light is formed on the paper. Until a very small patch. Until a very small patch of light is formed on the paper. Until a very small patch of light is formed on the paper. This is the method. Light is formed on the paper. Done. Look at the screen, everyone. What is the first one? Hold a lens to bright light and keep a paper in front of the lens. Then next one, adjust the distance between the lens until a very small patch of light is formed on the paper. If you want here itself in your tube, right? Parallel rays of light. Parallel rays of light. And this is what? A small patch of light, a very bright patch of light, a sharp spot of light. Very small patch of light. And this point is called what point? Focal point. Focal point. And then if you mark a curly bracket between the lens and this distance between the focal point and the lens is known as what length? Focal length. Hurry up, student, please mark this stuff. So the small patch of light is known as focal point, and the distance between the focal point and the lens is known as focal length. That right? The distance between the focal point, the distance, the vertical distance or the shortest distance between the paper and the lens is known as between a small patch of light. Between a small patch of light in the sense paper, ne? Between a small patch of light and paper. And the lens is known as the vertical distance between the small patch of light and the paper is known as what? Is known as focal. Is known as focal length. It's known as focal length. Is that clear? The vertical distance between the small patch of light and the paper is known as focal length. Not the paper, the lens. Sorry about that. Between the small patch of light and the lens. Lens is known as focal length. So this is how practically, experimentally, you determine the focal length of a convex lens. Focal length of a convex lens. Right? But you have to be very careful. Now, when you are using the laser torch, you should not point that towards some students. They play with this laser torch, laser beam. Actually, it can damage your eyes. You should never point that towards the eyes of some other students. And even the lens, when you use, you have to be careful, because if something happened to your eyes because of this, when you're going to study science, if your eyes get damaged, that is no use the rest of your life, right? So no point of studying and obtaining a degree or anything if you something happened to your eyes. So the number one is safety. When you're doing science, number one is safety. That's why even in the laboratory safety, it's very important, because it's not a good place to stay a longer period, as well as you have to use gloves and all the personal protective equipments you have to use. So lab coat, and you have to protect your eyes, so spectacles or something you have to wear. At least from the hardware shops, you have to buy plastic ones, and you have to protect your eyes. But if you have COVID-19 time, the ones that you have used, maybe the face shield, or you can reuse them. You can hand over that to your school lab, and then when you engage with the practicals, actually it gives an extra, because something happened, like can't help, like chemicals. It's not just burning. It's not just burning. Chemicals can damage the cells, and some of them can be even cancerous. That's why. Then next one is students. Shall I read this? Did you all finish copying down? Textbook also I explained these ones, and tutor also I have given because it's important for the exam. Next one, anyone still copying down? Raise hand. Done, right? Okay. Then next one, let's see how to draw the ray diagram for this. Okay, look at it. The first one already we have done it. The focal point is F, and all the rays parallel to the principal axis. What happened? Here the principal axis, and here the parallel rays. Rays coming from far away object called parallel rays. They all get converged to what? Not the second focus, first focus. Therefore, where's the object now? These rays are coming from which object? Far away object. We call it infinity. From the sun or moon, the object is what? At infinity. If you want to write near this one, number one is what? Object is at infinity. Where's the image? Image is format focal point. So that's what I have given students in the table. Look at here. It's already done for you. It's already done. It's a real image, because real rays, and it's inverted, is smaller than the object. So where's the image object now? At infinity. Where's the image now? At F. At F. So first one, I have done the table. I have done for you the table, the first one. But second one or not, you have to do it. Actually, nothing new. Don't memorize these ray diagrams, students. Learn the method, how to draw it. Okay, now we started from infinity. Now we put this what? Away from 2F. Beyond 2F. Where's the object now? Not between F and 2F. Don't worry about this F1, 2F1 and F1 because F2 and 2F2 means of F2 for the opposite end. F1 is the left side and right, left and right side to distinguish them. So AB is the object here. What is the object here? AB. What is the image here? A dash, B dash. So how to get this image? Ray of light parallel to the principal axis. What happened? Ray of light parallel to the principal axis passes through the focal point. According to rule 2, can you remember? According to rule 1, ray of light through the optical center travels straight. Where do they meet? They meet between F and 2F. Okay, Shahid, I'll explain. Wherever you keep the object. Okay, wait, I'll show you the video clip, then you will understand. Wait. So that when you keep an object in front of the lens, you have to start minimum 2 rays from the object to find the image, to find the position of the image. You need to start minimum 2 rays from the object. Minimum 2 rays from the object, right? That's what we discussed before rule 1, rule 2, rule 3. We use 2 of these rules and then we get the image, right? If you only you can use more than 2 or any number of rays, but at the end you should get the image at the same position, Shahid. Minimum you have to start 2 rays. Minimum you need to start with 2 rays because only from 1 ray you can't get the image. Okay. Okay, look at the screen now.
Okay, in today's video, I'm going to go over drawing ray diagrams for convex lenses. And this is going to be our general setup that we're going to use. And this is, I think, what you see most.
Can you all see the screen, students? Raise hand those who can see the screen now. Can, right? Okay, right. Okay, I'll play the video now. So let's see how to draw the ray diagram now. You can watch it again. Then after that, I'll go back to the result.
Here we have our convex or our converging lens. And we have some parts of this diagram I think that we should just be aware of. One of them is the principal axis. This is this white line that runs horizontal through the center of the lens. Then we have our focal point, and we have the point we call 2F. And the focal point is at a distance of 1 focal length from the lens, and 2F is twice as far away. So F is twice as far away. And this is a converging lens. And we have some parts of this diagram I think that we should just be aware of. One of them is the principal axis. This is this white line that runs horizontal through the center of the lens. Then we have our focal point, and we have the point we call 2F. And the focal point is at a distance of 1 focal length from the lens, and 2F is twice as far away. So F is from 1 focal length away, and 2F is twice as far away. And this is a biconvex lens, so there is an F, a focal point, and a 2F on each side of the lens. And what we want to be able to do at the end of this video is you should be able to draw the ray diagram to locate the image for any place that we were to put the object. So this green arrow is our object. We're going to start beyond 2F. Then we're going to put the object at 2F. Then we're going to put it between F and 2F. And then F, and finally inside of F. And for any case, you should be able to draw the ray diagram to locate the image. And you should also really know where the image will be beforehand. You should really know that before you actually draw the ray diagram. You should have a sense about where the image is going to be. You should have a sense about what the size of the image is going to be relative to the object, the orientation, and the type. Is it going to be a virtual or a real image? Okay, so let's go through and get started. Here is our first problem. You can see we have our object right here. It's at a distance DO, the object distance, greater than 2f, and we're going to draw the ray diagrams to locate the image. Now, before we get started, we're going to go over the convex lenses in this video, and then we'll do concave mirrors in the next video, and then concave lenses and convex mirrors finally in the fourth video. And you should really notice that for all of the ray diagrams, for all four of those optical objects, both mirrors and both lenses, the ray diagrams are really drawn basically exactly the same way. There's slight variations to how you do it, but we can use the same rules for all four of those types of lenses and mirrors. So you don't have to really memorize all of them. You just have to know how to apply the rules to each case. And in each case, the rules are basically the same. Okay, so let's get started. We're going to draw 3 rays to locate the image. This is the object, this is the lens, this is your eye. We have to draw 3 rays that come through the lens in the direction of your eye so that you can locate.
Now, Shahid, DO is object distance. DO is object distance. That means that the distance from the object to the lens. That is called DO. Okay. And what is this? This is the object. So object can be you can light up a candle here. If you have a hand lens in your house, hand lens magnifying glass, you can do this. You can light up a candle and you can draw, you can on your table, you can have a rule or meter rule, or like even you can have a paper and you can keep the, okay, can you all hear me? Now you can move the candle. You can keep this side white paper, the screen, and you can check whether you can get this image to this side. You will get the candle here, the image on the screen, or the white paper or cardboard. You can keep here the screen here. This side you can get the image. So gradually you move this candle towards the lens, little by little, and you bring this from away from 2f to 2f. Then you keep the candle between f and 2f. Then you keep the candle at f. So then the object distance, you are changing the object distance. Then you get different images on the screen the other side. That's what they are doing it. You have to do this in the school as a practical. So what is DO now? Object distance. Now where's the object? Object is away from 2f. Did you get it, Shahid? Understood? DO is object distance, right? I'll play the rest of the video now.
Locate the image. The first ray we draw is the parallel ray. It enters the lens parallel to the principal axis. So once again, this is the principal axis. This is the first ray. You can see those two are parallel. We draw the first ray parallel. When it comes out of the lens, it's refracted or bent in such a way that it goes through the focal point. It must go through this point. It's not just some random bend. It goes through the focal point. So that's the first ray. I like to call this one parallel F. The next one is kind of the opposite. It enters the lens going from the object through the focal point. So it must go.
You learn 3 rules, ne? Parallel passes through the focal point, refracted parallel. And the one is what? The one through the optical center, travels straight. If you want, you can combine all 3 rules in one ray diagram and get the image. Because from one ray, you can't get the image. But minimum students, you need 2 rays. But you can do this with 3 rays also, maximum 3 rays. But even with 2 rays, you get the image. So in your textbook, they have only 2 rays from the object item. Right? From the always remember, when you draw the ray diagram, you have to mark the direction of the light rays like this. Otherwise, no marks in the exam. You mark from where to where light rays always starting from the object. This is always object. Light rays begin from the object, and again it undergoes refraction after the lens. So then you have to check after the refraction at which point they meet. Got it? Okay, now let's continue. I'll play the rest of the video now. Learn one ray diagram properly. all the 6 also the same principle, same scenario, same method we follow. Mohammed, you have a question to ask, or I don't know, I raise hand, or I used to copy down. If you want, you can take a screenshot of, like, I will share the recording if you want, no problem. You can send me a request out of the class if you want to reverse this.
Both the focal point. It starts at the object, goes through the focal point, strikes the center of the lens, and comes out parallel. So this one I like to call parallel F. And the third one is the one we draw that goes straight through the center, and the image is going to be located where those light rays converge, and that is our image. Okay? Now, we want to summarize where is the image and all the information that we want to know about the image. In this case, when the object is greater than 2f away, the image will always be somewhere between f and 2f. The image will always be smaller than the object. The image will always be inverted or upside down, and will always be a real image. Okay? So we've completed that problem. I'm just going to review this one really quick, and then we'll go on, and we won't take as much time for the next ones, because we've got 4 more to do. So we drew the ray diagram. We drew the first ray, parallel F. Then we went F, parallel, has to go through F, has to go through F, has to be parallel, and has to be parallel to the principal axis. This one goes that we got from our ray diagram. F, parallel, straight through the center, and that is our image. You will notice when the object is at 2f, the image will always be at 2f. The image distance is 2f.
Now look at here, the next one. This is what we are going to discuss next. When the object now, where initial one, where's the object? Beyond 2f. Greater than twice the focal length. Up to f is focal length, students. Up to 2f is what? Twice the focal length. Now the object is what? Away from 2f. Beyond 2f, greater than twice the focal length. What? Object distance, DO now. Where's the image? Image has come between f and 2f, the other side. If you keep a screen here, a white paper, or like a cardboard, you can get this image. If you light up a candle here, students, you can get the candle flame upside down. The candle you get upside down here, and like this. Did you get it? That means this image is real. Why? We can capture that to the screen. And this image is upside down, inverted. And this image is formed between f and 2f. And this image is smaller than the object. That's why we call it diminished, a small image. The image height is less than the object height. That's why we call it a small image. Understood now? Right. Okay. Then next one, what has happened? Now you gradually, from where did we start? We started from infinity. Then beyond 2f. What is the next position? At 2f. What is the third one? When you come to the next ray diagram, what? You keep the object between f and 2f. Next one, we keep the object at f. And later, you keep the object between O and f. So that's how you get 6 ray diagrams. Then you get 6 different positions of the image. That's why you are getting 6 ray diagrams for the convex lens, students. But if you take concave lens, you got only 1 ray diagram, because even though you change the object position, image properties won't change. But here, the properties of the image changes with the position of the object. That's why you get 6 different ray diagrams. Understood? Now, so where's the object now? At 2f, at 2f. So shall you complete this in your tutorial? So hurry up. Okay, this is where. Where's the object now? Beyond 2f. Here 2f, beyond 2f. Object between f and 2f. This image is what? Small. Here the height is more, right? Here the height is less. Small, real, inverted. Shall you complete the ray diagram, the table now? For the ray diagram 2, let's complete the table, students. The same page below, because in your textbook, you will find these ray diagrams in different pages. But I have given all the ray diagrams in one page so that you can easily study this. Where's the object now? Where's the object? Beyond, complete the table. Beyond 2f. Beyond 2f. Image between f and 2f. Between f and 2f. So what are the properties? Real, inverted, and smaller than the object. But the object position is different. No? That's why I speak about new ray diagram. Ray diagram number 3. Okay, shall I write this? Did you all finish copying down? It's not difficult, but in the textbook they have given beyond 2f. Instead of beyond 2f, the textbook also they have given a similar table, but they have given greater than twice the focal length. In the textbook they have given greater than twice the focal length. Greater than twice the focal length. Understood? Right. Then I'll erase the screen. Next one is, students, where's the object now? Ray diagram number 3. Ray diagram number 3, where's the object? At 2f. At 2f. At 2f. Image also at 2f. That's what we discussed in this video also. Can you see this one? Object distance is what? 2f. Image distance also 2f. Di means image distance 2f. At 2f at 2f. But opposite side. Image is in the left, object left side, image right hand side. Remember, for lenses, if they are at two different ends or the opposite ends, real image. But if the object and the image, if they are the same side, it's virtual. Again, I'll repeat. For lenses, if they are opposite end, real. If they are the same side, virtual. For lenses, for mirrors, the same thing, opposite. Mirrors, same side, real. If they are opposite end, virtual. Opposite. Right? The mirrors and lenses, right? So this is same as, like it's parallel to your concave mirror. Also, you get the same thing at C. Can you remember? If you can check the mirrors, concave mirror, they are we call what? At C. The same properties. Here the lens, they are mirror. That's it. Concave mirror also, you got 6 ray diagrams. They are almost parallel. Nicely matched. Only thing is what? That is reflection. This is refraction. Okay, now let's see, because that is this. I know the optic lesson is one of the hardest lessons for the students because they try to memorize ray diagrams one by one, but don't do it. Learn the method how to draw it. Now, my advice: if you have 2 different colors highlighted, students, now you better use 2 different colors and write parallel one passes through the focal point. One color. Okay, I use red here, and you can use a different color and write what through the optical center. It goes straight. But if you want these 2 rays enough to get the image, but in that video clip also they have shown. But if you want, you can draw one more like this. What? A ray of light through the focal point. The third rule, through the focal point, what? Refracted. And anyway, all 3 rays meet at the same point at 2f the other side. But you don't need to draw 3 rays, minimum 2 enough. It's given marks. You are given marks in the exam, right? Okay, shall you complete this in your tute now? In your tute, table number 3. Where's number 3? The third ray diagram. If you write ray diagram number 3 here, right? Where's the object? At 2f. At 2f. Where's the image now? At 2f. At 2f. What are the properties? Real, same size as the size of the object, and inverted. That's it. So previous one is smaller than the object. This is same size as the object. But the point. Shall I erase the screen? Done. Anyone still writing? Raise hand. Okay. Are you still copying down? When you're done, please lower your hands, right? Others, can you complete the 4th one? Now, after 2f, what happened? Between f and 2f, then you bring the object or the candle bit more closer to the lens. Then what's the next position? Between f and 2f. Image you can check. That will be beyond 2f. Yeah, very good. Okay, very good, Muhammad. Image will be beyond 2f. Let's see the ray diagram. Shahid, are you done? I'll give time again to do 4th one. Look at number 4. Where's the object now? Object is kept what? Between f and 2f here. I'll highlight the pink. This 2f, this f. Between f and 2f, the same principle. What? Ray of light parallel to the principal axis passes to the focal point. Ray of light through the optical center goes straight. Don't memorize. Just remember how to draw the 2 rays from the object. Parallel one through the focal point, through the first focus, not the second focus. Through the optical center goes straight. Where do they meet? They meet beyond 2f. Object between f and 2f, image beyond 2f. So this image is what? Magnified. Look at the height of the object. Object height and the image height. Image is what? Magnified. This is what we use in projectors. Magnified image. But disadvantage is it's being inverted. So shall we complete the table now? Here's the object. Object is ray diagram number 4. Object is between F and 2F. Where's the image? Beyond 2F. Beyond 2F. And what are the properties? Real, magnified, and inverted. This magnified is a bit important. Real, magnified. So if one property change, it will become a new ray diagram. If the position change and the previous one, it become a new ray diagram. Got it? So now, what is the next place? Now we bring the candle or whatever the object bit more and more closer to the lens. After between F and 2F, what? Now to the next closest place, F. When the object is, look at ray diagram number 5 now. When the object is kept at F, image is formed at infinity. The same principle. Ray of light parallel to the principal axis passes through the focal point. Ray of light through the optical center travels straight. So it's like a railway line. Where do they meet? Will they meet near the lens? No, they will meet. We assume they are going to meet at infinity. So therefore, images appear to form at infinity. Real inverted is small image, but this image is diminished. You don't get a clear image. I think textbook also they are given this blank. You don't get a clear image close to the lens. So to get this image, you have to go to infinity. Right? That's why we don't write the properties for this. The last ray diagram students is almost 9 o'clock, 9:05. Last ray diagram, that is the most important one. This is the only ray diagram which gives erect image. This is the only ray diagram which gives erect image. And this image is dotted line means what? Virtual image. All the others are real images. This is the only virtual one. All the others inverted image. This is the only erect one. And this is used as the hand lens. Letters get magnified and letters are erect. You can read them without any difficulty, but you can't capture that to separate screen since the image is virtual. So this one I'll explain again next week. This ray diagram is the most frequently asked ray diagram in the oral paper as well as term test. Put 3 stars near ray diagram number 6. Out of these 6 ray diagrams, what is the most frequently asked ray diagram? Ray diagram number 6. So I'll explain this again, students, next week. I want you to draw this in your book also. And after that, we have discussed only the last 2 pages, applications, right? Applications. Where are we using this? In which devices we use these lenses, right? If possible, try to answer the all the remaining questions of this last few pages. There are a lot of practice questions, students. Try to answer them at home. I'll discuss them in the paper class. And next week, I'm going to start Unit 6, Biology, digestive system also. Within 1 hour or less than, it will take less than 1 hour to complete the remaining part, the last ray diagram and the applications of convex lenses, right? Okay, then I will stop for today. Good night and God bless you.